In this video, we're going to discuss Friedel acylation. But before we get there, I want to take a brief look back at the alkylation process that we've discussed before. So here's a reaction. We have toluene and we want to add this propyl group. We have our aluminum trichloride product. What are we going to get? Well, of course, we've already done this in class. You know what that is. I'm trying to trick you. There's a rearrangement because you can't form a primary carbocation. So what's the product? Well, it's going to be a mixture of B and D. Now, there's some steric blockage here in the orthoisomer, so we're probably going to get mostly D. So we're making, how does it work? We pull off the chloride. As the chloride leaves, we have to have a hydride shift to give us the isopropyl rhenium ion, which is, of course, going to lose the proton and form the para-isomer, where we've added the isopropyl group there. So adding an N-propyl group straight chain is not so simple. Now, how could you do that reaction? Well, let's come up with another scheme. How could we make the primary derivative? Well, of course, the answer is to use acylation, which is the subject of this little video. So what is acylation? Well, acylation is just starting with the acid chloride. The acid chloride, actually, pulling off that chloride is a lot easier than pulling off the chloride on an alkyl group. And the reason is that the resulting cation is more stable. So if we grab that chloride, follow the arrows, what we get is this weird looking thing, carbon oxygen with a triple bond. This is called an acylium ion. These things are actually pretty stable. And you've seen a similar molecule for a long time, and that's simply carbon monoxide. So think of an acylium ion as simply as like a carbon monoxide with a alkyl group coming off that carbon, and that doesn't seem so unreasonable. So carbon oxygen triple bonds certainly exist, and acylium ions have a reasonable amount of stability. In fact, they're pretty easy to form. So any acid chloride, throw in aluminum trichloride, you'll form that acylium ion. But I said it's reasonably stable, but of course it is still very reactive, and it'll very readily react with a benzene ring. Now, so let's see how this works. We add our the acid chloride of propionic acid, and we get our acylium ion. That acylium ion will react with the toluene, giving us again an rhenium ion. And the same thing, that rhenium ion, it has a certain amount of stability now because of the presence of that methyl group. So the methyl group actually makes this reaction go a little bit faster because it's donating some electrons, which can help stabilize the resonance structure down here. Now, of course, we lose the proton, and there we go to our product. So this process works pretty well, but of course, we don't have the propyl group yet. We've got to get rid of that carbonyl. So how do you reduce the carbonyl? Well, this video isn't going to discuss this very much, but there are actually two methods that one can use. One of them is the Clemson reduction. Clemson reduction uses what's called a zinc-mercury amalgam, where you take zinc metal, add a little bit of mercury to it, presence of HCl. This will reduce the oxygen down. This is an electron transfer reaction. It's fairly complicated. It's discussed in the textbook, page 494. There's another method as well, which is called the Wolff-Kishner reduction. This is a fun mechanism. You might want to look it up because it ends up producing dinitrogen, and it also works. Now, there's some limitations on these two reactions. Is that the Clemson reduction only works if there's an adjacent phenyl ring, because it involves electron transfer, and that phenyl ring is important for that electron transfer process. The Wolff-Kishner is a more general reaction, and you can do this on any ketone or aldehyde. So you have two different ways of doing it. Okay, so how could you make this molecule for starting with benzene? So putting on benzene, we got to put on a methyl group and a propyl group. Well, if we just methylate, in principle, we can go to toluene. That seems straightforward. We could then take that and add the acid chloride. So this looks like a good route. There are, and then of course we reduce. So there are some possible problems, however. One is that in principle, if you think about it, you put the methyl group on the benzene, but the methyl group is donating electrons. So that means putting on a second methyl group is actually easier than putting on the first one. So the one problem is that you can get what we call polyalkylation, where you put on the methyl twice. Another problem is that when you do this direct acylation, you're going to get a mixture of ortho and para, and you can have this ortho that you're going to have to throw away. So you have two possible problems here. Multiple additions might be a problem, and you might have a lot of ortho to throw away. Now, could you live with this? It's a matter of yield. If you control things right, you might get the toluene as the major product. And this thing here, again, the para is probably the major product. There's some steric problems with the ortho. So you'd get some of this, and maybe that's good enough. But could you improve the synthesis by changing the order of the reaction? So what if we did the acylation first? So you do the acylation first, then do the methylation. So would that work? Well, no, it doesn't work. Why doesn't it work? Well, it's because this carbonyl is an electron withdrawing group. And the electron withdrawing group makes the benzene less reactive. And it turns out these Friedel-Crafts reactions are more difficult to do than, say, simple addition of bromine. And having an electron withdrawing group on your ring will shut down Friedel-Crafts reaction. So this reaction simply doesn't work. Or if it does work, it gives a very poor yield. So let's assume that we do get a poor yield. Well, the problem is the poor yield wouldn't give you what you want either, because the directing effect, if you remember this when we talked about the DCl exchange, the directing effect with an electron withdrawing group would send the methyl to the meta position. So you wouldn't. So it's this reaction has double problems. You wouldn't expect much because of the deactivation, and if you got any at all, it would be the wrong isomer. So this simply doesn't work. So the trick, of course, is to reduce first. Reduce first to the propyl group, then do the methylation. Now, again, this methylation could give you some ortho product, but now this propyl group is pretty big up here, and so there's a steric incentive to go to the para position, so your yield is probably going to be pretty good. So that's a pretty good illustration of how playing around with these different groups, you can get different reactions or get different patterns of substituents, and you just have to stop and think about it. The general rule is Friedel-Crafts, either alkylation or acylation, are not that good of reactions in terms of they need a fairly reactive benzene ring. Any deactivation will shut them down. And the directing pattern is if an alkyl group is on the ring, you expect ortho-para substituents. If you have an acyl group on the ring, it'll shut down reactivity for Friedel-Crafts completely. Other things will also, if you do something like bromination, that'll go meta. Okay, so let's do one final problem here. Here I have this is an ester. It's a phenyl ester of benzoic acid, and we're going to do Friedel-Crafts alkylation. Now we don't have to worry about rearrangements because it's an ethyl. If an ethyl rearranges, what do you get? You get an ethyl. So the question is merely where does the ethyl go? So let's think about the various possibilities. It could substitute on the ring at the left. You could either get the ortho product, or you could get the para product over here, or the meta product, or the para product. Now we know that the acyl group is electron withdrawing, so the reaction is not going to go well here at all. It's going to shut down this reaction. And if it did react, you would get B, but you wouldn't. But B would be very low yield because it's being shut down in terms of reactivity. Because this would be a meta director, but it deactivates, so you're not going to expect a good yield. Any small yield you might get would be B. Over here, on the other hand, oxygen is an electron donor. The lone pairs of the oxygen can feed into that ring, making it more electron rich. So going into this phenyl group is preferred. Now, where does it go? Well, it goes ortho or para. But if you look here, the ortho substituents, you have to deal with this benzoic acid group over here rotating around. The benzoate's fairly big. So those ortho positions are going to be fairly blocked which says that the para position is definitely going to be preferred. So where's our compound? Well, it's F over here. So that is certainly what you would predict. And so thinking about these different factors, you can usually figure out exactly what's going to happen. So let's draw it out. We go there, and there is our final product. As we here's the stabilization from that oxygen, and now we pull off the proton and we go to our product. So that's a pretty good scheme, and it shows you the power of these syntheses if you plan them right. The answer, of course, was F. Okay, thank you.